We talked earlier about how we can estimate changes in enthalpy of reaction by using heats of formation. There's a question about that on experiment 7B lab report. We can also do this using individual bond energies. So the bond energy is the energy needed to break 1 mole of the bond in the gas phase. So bond energies are always going to be positive. It always requires that you put energy into the system to break the bonds. If bond energy was negative, then atoms would just fall off on their own, and then why would they make a bond in the first place? They wouldn't. So we say that a bond is stronger if it takes more energy to break. This is just, kind of common sense. So compounds that have stronger bonds tend to be more stable and less reactive. Compounds with weak bonds tend to be less stable and more reactive. So the average bond energy is the average of bond energies in a bunch of different compounds. And we need to do that because the energy of a given bond will vary slightly depending on what molecule it's in. Here we're looking at a carbon-hydrogen bond. And here we've got CH3 with a hydrogen on it, so we're looking at this carbon-hydrogen single bond. If we swap those hydrogens and put fluorines or bromines or chlorines, the energy needed to break the bond changes a little bit. 438, 446, 402, 401. We're not going to be concerned about why that changes or what direction, but it can be different. So we're just going to be concerned about an average bond energy. And then it kind of makes sense. A double bond is going to be stronger than a single bond. And a triple bond is stronger than a double bond. So double and triple bonds are going to have higher bond energies than single bonds. Bond energies are not something you memorize. You go look them up in a table when you need them. And so this is a table from your textbook. When you're looking up bond energies, make sure that you've got the correct 2 elements and the correct kind of bond. So for a lot of these, carbon-carbon, there's 3 different possibilities. Carbon-nitrogen, 3 different possibilities. Could be single, double, or triple bond. And one I'd like to point out to you that's a little weird, there's an asterisk here. Carbon-oxygen double bond, the average is 736 unless you're looking at CO2. It's 799 in CO2. And everybody else just kind of acts normally. Yes?
If we get testimonies on the exam, will we have this chart?
Yeah, you never memorize these.
Okay.
No. You'd probably be given the bond energies that you need.
Okay.
So we can estimate the enthalpy change by thinking about taking the reactant molecules apart, breaking some of their bonds, and then putting them back together, making some new bonds. So bonds breaking is endothermic, putting energy in. So those are going to be positive numbers. Bonds forming is exothermic. When a bond forms, it releases energy. So there you look up the bond energy and you change its sign because that's what happens. It's the opposite of breaking. It's making. So to find the enthalpy change for the reaction, we're going to add up all the bonds that are broken and all the bonds that are formed. Here's an energy diagram showing how this might happen. So here we've got methane and chlorine reacting to form chloromethane and hydrogen chloride. So in order for this to happen, we have to break this chlorine-chlorine bond. We could look up that energy. We're going to have to put energy in. Energy of the system goes up. And we're going to need to break one of these carbon-hydrogen bonds. So that will also require putting energy in. So that would be the sum of those 2 bond energies. Now we have the pieces that we can put back together. And we're going to put chlorine with hydrogen. So we're going to make a hydrogen-chlorine single bond, and the other chlorine is going to bond to this carbon, and so we're going to make a chlorine-carbon bond. And we take those bond energies, flip them around, make them negative, and we add all these up, and we get delta H for the reaction. Any questions? Sometimes we say that energy is stored in chemical bonds, and that's really kind of a little off. Breaking a chemical bond requires energy, so it's not like you can break open the bond and get the energy out of the bond, right? But an energy-rich compound can undergo a reaction where weak bonds are broken and strong bonds are formed. When the strong bonds are formed, it releases energy. So it's not really that the energy is stored in chemical bonds, but that we get energy when we form chemical bonds. It's always the forming of the bonds that releases the energy. Yeah.
No,
Okay.
sorry.
That's okay.
Okay, yes, please.
Okay.
Sorry, will you kind of say that chemical bonds just carry potential energy?
Yeah, we could kind of, I think that is a better way to say it. The chemical bonds are potential energy, and we see the energy coming out into the system when those bonds get formed, not when they're broken. And you can kind of think of this like investing. You know, if you want to make some money, you can't just like start with nothing, right? You have to invest some money and get a return on that money, right? So here we're investing by breaking chemical bonds, and we're getting a payout when new chemical bonds are formed. Whether this is endothermic or exothermic depends on which takes more energy. Was this a good investment? Am I getting more out than I put in? Or is it a bad investment? I put a whole bunch of energy in to break these bonds, and then I just made a few little weak bonds, and now that energy's gone, right? It can't actually be gone because energy can't be destroyed. Right? So let's look at this question. The reaction between hydrogen and oxygen to form water is highly exothermic. Which statement is true of the energies of the bonds that break and form during the reaction? There's a lot of words here for these three choices, and they are mostly the same. So the first one, the energy needed to break the bonds is greater than the energy when the new bonds formed. B, the energy needed to break the bonds is less, or the energy needed to break the bonds is about the same. So hydrogen and oxygen forming water is exothermic, meaning it's releasing energy. It'll actually like make an explosion. So is breaking the bonds higher in energy, or is making the bonds higher in energy? Making the bonds. Because in the making of bonds, energy is released. So the energy needed to break the bonds is going to be less than the energy released when the new bonds are made. Any questions about that? Okay, so here's an example of how to calculate delta H from bond energies. Potential future fuel is methanol. Write a balanced equation for the combustion of gaseous methanol and use bond energies to calculate the enthalpy of combustion of methanol in kilojoules per mole. Okay, so this is kind of a long problem because they didn't give us a chemical equation, and they're making us go look up all the bond energies. So the first thing we have to do is we need a chemical equation for the combustion of methanol. So we've got the formula there. Let's write it with a regular pen. CH3OH. And if it's burning, what is it reacting with? Oxygen. And what will it form? carbon dioxide and water. So that's something that we should know. Now we need to balance it. So there's one carbon on this side and one carbon on that side, so that's fine. Over here I've got 3 hydrogens and 1 hydrogen there. Over here I've got 2. So a total of 4 on that side. So if I put a 2 in here, then my hydrogens are balanced. And then there's literally oxygen everywhere. So we've got 1 oxygen there, and we've got 2 here, and we've got 2 and 2. So we've got a total of 4 over there, and 3 on this side. We don't want to change the subscript on methanol because that'll mess up the hydrogens, and we have to basically start all over. But how can we get 1, because we need 1 more, right? How can we get 1 oxygen atom out of this molecule? Well, we can't out of 1 molecule, but we could have half a mole, right? Half a mole of oxygen. So if I had half a mole of oxygen, like how many shoes are in half a pair of shoes? 1, right? So half of this pair would be 1, and now I've got 4. Now, is that how we want to write this chemical equation? No. We want to avoid fractions. Well, to get rid of this fraction, if I multiply this by 2, the fraction goes away. So I need to multiply everything by 2. So I'm going to multiply this by 2, and that becomes a 1, and this becomes a 2, and that becomes a 4. Now I've got, I'm going to double check this because this is not looking right. Now I've got 4 and 8 is 12. Yeah, I didn't want a half there, I wanted 3 halves because I needed the original 2. So I need a 3 in here is what I need. There's 2 here, and 3 times 2 is 6. What the heck did I do? Yes, that's what I did. I got the 4 and I took the 2 from hydrogen. Thank you. That's just 4. That's 8. So 2 plus 6 is 8, and 4 plus 4 is 8. Ooh. That was ugly. Bye-bye. There's your balanced chemical equation. Now, if we had models, we could maybe do what was done in that diagram, where we figure out exactly which bonds need to break and exactly which ones need to be made. That requires a lot of thinking, and sometimes it's easier to just do the sort of rote way, let's just do all these chug, 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 instead of let's trying to think about how we can do that shorter. So what I recommend is we're just going to think about taking our reactant molecules and breaking all the bonds. Just break them into individual atoms, and then over here we're going to put them back together. So we need to know what bonds are there, what bonds are being broken, and what bonds are being made. So we need Lewis structures. So, not reviewing Lewis structures here. This is the Lewis structure for methanol. This is the Lewis structure for oxygen. Over here we've got CO2. H2O. As it is, this problem would be a great worksheet problem. Worksheet problems are hard, right? If this was an exam question, it should start more like from this point. Because I'm going to test you on, can you write the equation? Can you balance an equation? Those are separate questions. Can you write Lewis structures? That's a separate question. I want to stick all of those in one problem on an exam. So now let's look and see what we've got here. Well, to take this guy apart, we're going to have to break some carbon-hydrogen bonds. So there's 3 carbon-hydrogen bonds in 3 moles of carbon-hydrogen bonds in 1 mole of this compound. Yes? And we have 2 moles of it. So that's, that doesn't work. 2 times 3 CH bonds. We also need to break a carbon-oxygen single bond. How many of those are in that molecule? Carbon-oxygen. There's 1 in the molecule, or 1 mole in a mole, and then there's 2. So there's 1 in the structure, and then I'm multiplying by 2. And then we have oxygen-hydrogen bond. How many of those are in that Lewis structure? There's 1, but we've got 2 moles of the compound. That make sense? And then we've got the other reactant. So this has an oxygen-oxygen double bond. There's just 1 of those bonds in this structure, but I have 3 of them. So 3 times. I'll put a line down the middle because it gets kind of mixed up after a while. So let's go over here to the other side. Here I've got carbon-oxygen double bonds. In the 1 structure, I have how many bonds? 2. And how many of that structure do I have? 2. And then in my water, let's see, what colors do we have left? Purple. So I've got oxygen-hydrogen bonds. And how many are in 1 of these molecules? 2. And how many of the molecules do we have? 4. I have 4 water molecules, so that means I'm going to have a total of 8 of those bonds that are going to get formed. So now we need to look up the bond energies. So we're going to go back to this table. And we had carbon-hydrogen bonds. Those were 414. And these are all kilojoules per mole. So that's that guy right there. And there were hydrogen-oxygen bonds, 464. There was, there was a carbon-oxygen single bond, 360. There was oxygen-oxygen double bond over here. 498. And we had carbon-oxygen double bond. And that was in CO2. So 799. Did I miss any? Yeah.
Can you go back to the oxygen? Like the balloon is like 1 or 2?
It's one double bond.
Just one double?
One double bond. Yeah. Hmm?
Why? Why is not like 2?
Hang on just a minute. Did I miss any? Okay. So this is a double bond. And we have 2 oxygen atoms, and there is one double bond between them. We're not going to call this 2 single bonds because single bonds have a different energy, and the energy of one double bond is not twice a single bond. So there's just one double bond in here, and then we've got 3 of those, so there's a total of 3.
Oh, why was C double bond? Oh, that one's 799.
Bec-
Wasn't it 736?
Good question. Oops, I'm really lost. So carbon double bond oxygen is 736, but there's an asterisk. It's 799 in CO2, and the bonds we're looking at are in CO2.
They're a little more complicated. Is there a reason for that, or
Well,
complicated?
there's a reason that that one is sticking out is because we run into CO2 a lot, and the difference between that bond energy and most of the others is so different that they decided to not just lump them all together.
So does that happen pretty regularly though, where bond energies can be different, like depending on the?
Bond energies are always different in different compounds.
Okay.
Yeah. So that's what we were talking about right here. So
Oh, okay.
carbon, hydrogen, in 4 different compounds, they're all a little different.
Okay.
So we just average.
Okay.
Okay, so now what we need to do is write down the bond energies. So the carbon-hydrogen bond was 414. And so what we've really got going on here is 2 times 3, a total of 6 moles, and 414 kilojoules per mole. So when we multiply those, the moles are going to cancel out. Down here I've got 2, and the carbon-oxygen bond was 360 kilojoules. Actually, let's do this. And I have 2 of the oxygen-hydrogen bonds, 464. And I have 3 of the the oxygen-oxygen double bonds. So then I can add up all the energy that I need to put in here to break up everything. So 6 times 414, 2484. 2 times 360, 720. 2 times 464, 928. 3 times 799. 2397. This is definitely not a problem you should try to do in your head. I would really, really struggle doing this in my head. So if we add all these things up, please check my math. I'm getting 6529 kilojoules. So, yes.
I don't know if it's, I can't read it or not, but you double bonded oxygen, say 498 on the board.
Thank you. I used the wrong one. Yeah, I was looking at the CO, so thank you. So this is wrong. Actually, let's do it like this. So I needed the oxygen double bond, which was 498. 498 times 2. 996 plus 928 plus 720 plus 2484 5125. Did I make any other mistakes? Yeah.
You mostly said 498 by 2.
Like two instead of
Yeah.
It's okay, we're all tired, don't worry.
Did you have your cookies before class?
I did actually, but they were red velvet cookies, which is like the least favorite of all the cookies that they
I
have.
love red velvet.
Okay,
1494.
3 times 498. 1494. Five, 6, 2, 6. Third tries the charm, right?
My favorite number.
Okay, that was not easy. So now we're here. 2 times 2, I've got 4 moles of these carbon-oxygen bonds, the ones I was trying to use earlier. Here I am making the bond. So I changed the sign on the number. This is releasing 799 kilojoules. And I have 8 oxygen-hydrogen bonds minus 464 kilojoules. Oops, don't want to do that yet. Negative 799 times 4. Negative 3196. 8 times negative 464. Negative 6908. Did I do that one right?
Mm-hmm.
Phew. A little worried about myself there. So I'm going to add these two numbers together. 5626 kilojoules plus negative 6908 kilojoules. Negative 1282. That is delta H for this chemical equation. Any questions? Bond length and bond strength are typically related. So we were just talking about bond energies. Let's look also at bond length. So an average bond length, the average length of the bond between two particular atoms in a large number of compounds. Double bonds are shorter than single, and triple bonds are shorter than double. So here we've got a little table showing the bond length from a triple to a double to a single is getting longer. And here the bond strength is getting smaller. So you could think of this as like 3 rubber bands holding the carbons together versus 2 rubber bands or 1 rubber band. And 1 rubber band is going to stretch more easily. So these will be a little further apart. And if you're trying to break them entirely, you can break one rubber band easier than breaking 3.
That makes sense.
Yeah.
Does this have to do with Coulomb's law that we
I think it does have a little bit to do with Coulomb's law.
I remember as they get further apart, they get weak. The force
Yeah,
of
because the attraction is greater when the charges are closer together.
Okay.
Yeah, I think that's related. Any other questions? It's a table of average bond lengths. I'm not even sure why that's in there because I don't think we use it at all.